Good morning, all of you. Today we are going to learn about real numbers. In the real numbers, we are going to learn about the fundamental theorem of arithmetic. Fundamental theorem of arithmetics. This is theorem 1.2. So before going to this, we will discuss about the some basics. So in the ninth class, we have studied about different numbers, natural numbers, whole numbers, rationals, irrationals. Of course, we have studied mostly all the numbers, but here we will just discuss about the some properties of the natural numbers. Natural numbers. Suppose if we take natural numbers, see in the natural numbers we see different numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you write all the factors of these numbers, so what you observe is that one has factors only one, two factors 1 and 2 because 1 into 2, three factors 1 into 3, it has two factors, four factors 1 into 4 we can write 2 into 2, so it has factor 1 into 2 and 2. 5 factors 1 and 5, 6 factors 1 into 6, 2 into 3, so it has 4 factors 1, 6, 2, 3. Now take 7, 7 factors 1 and 7 because we can write only one way. 8 factors we can write 1 into 4, 1 into 8, 2 into 8, 2 into 4. So this is 1, 8, 2, 4. 9 factors we can write 3 into 3 means 3 factor 1 into 9. 10 factors 2 into 5, 1 into 10. So these are the different factors we are observing for some numbers. So we can take so many numbers, but I am taking only this some examples for discussing the some properties of the natural numbers. In these all numbers, we know that some factors has exactly two factors like 2, 3, 5, 7. So these numbers has exactly two factors. So such numbers are known as prime numbers. Such numbers are known as prime numbers. Prime numbers. So in the natural numbers, whose numbers has exactly two factors, that numbers are known as prime numbers. See that some other numbers, you see that some other numbers like 4 factors are 2, 4 has 4 factors, 6 has 4 has 2 factors, 1, 4, 2, 6 factors are 1, 6, 2, 3, 4 factors. Now 8, 1, 8, 2, 4. So it has 4 factors. Like 9. 9 factors, how many are there? 3, 1, 9. It has 3 factors again. So it is also more than 2 factors. 10 also more than 2 factors. So some numbers, prime numbers, we can give example 2, 3, 5, 7 and so on. Now, so these other than prime numbers, we can see some numbers has more than 2 factors. Such numbers are called as composite numbers. Such numbers are called composite numbers. So what are that numbers? 4, 6, 8, 9, 10. These are some examples for composite numbers. And see that actually see that see number 1 is has exactly one factor it has, so that its number is not called as neither prime nor composite. We already know this concept, but we discussed about some properties. So here we can clearly understand one concept, that is a composite numbers. See that composite numbers 2 and 5 has two prime factors, 9, 3 into 3, 8, 2 into 2 into 2 we can write, like 6, 2 into 3, 4, 2 into 2. These are the product of the primes. So these are the product of prime number. Still we can get for if any like this prime factorization for any composite number. Not only for these numbers, if you take suppose 20 is there, 20 how can you write 20 is a composite number, you can write 2 into 2 into 5, that is 2 square into 5. So that some numbers, some composite numbers, even for every composite number, we can express it as a product of power of prime numbers. Every composite number can be expressed as the product of the powers of the primes. So this concept is nothing but the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Every composite number can be expressed as, otherwise can be factorized as product of the powers of the prime numbers. And this, and also we can see that one more property, and every composite number can be expressed as product of primes. Also we can see the a different factorization for this factorization is unique. This factors 2 square into 5, we cannot get this kind of factorization for any other number. 2 square into 5 only exists for the 20 only. For example, 10 there, 2 into 5 can be, the 2 into 5, we can't find any other number. Only 2 and 5 can be possible, only 10. 3 into 3 can be possible for only 9. 2 into 2 into 2 can be possible for 8. So that this factorization is unique. This is unique factorization. So that every composite number can be expressed as a product of primes, but also the factorization is unique. So to know every number has different kind of factorization. So that even we can consider its order also. Even if we change the order also, we will not no problem at all. Apart from its order. So in 2 into 5 or 5 into 2, no problem. Here 2 into 3 or 3 into 2, no problem. But these numbers whatever present in this factorization, that are present only for that particular number only, no. For no other number it has no such kind of factorization. So this is unique. So finally what it is telling, that the definition I will write here. Definition is fundamental theorem of arithmetic definition. Fundamental theorem of arithmetic. What is the definition we will discuss finally. So every composite number can be expressed or factorized as a product of primes. Every composite number can be expressed as a product of primes, and this factorization is unique. This is unique factorization. And apart from the order in which the prime factor occurs. So the prime factor order is not important, but that whatever the prime factor is unique. It is different for every composite number. It is telling about the fundamental theorem of arithmetic. So using this one, we will discuss some problems, because the application part of this theorem is will discuss. Suppose there is a one kind of problem like 4 power n, where n is a natural number. Where n is a natural number. So what is the problem? In the problem, what we have to find, the 4 power n, where n is a natural number, we have to check that whether 4 power n can be end with 0 for any natural number n. For example, if you take some numbers for n, so whatever the numbers we can take for n, you can take for any natural number like 1, 2, 3, whatever that. For example, if you take 1 equal to 1, so 4 power n equal to what? 4. If you take n equal to 2, 4 square equal to what? 16. If we take n equal to 3, 4 cube equal to 64. So we will try on this way, and we will until we get 0 or not. So but this is a long method to verify this way, because there are so many numbers, there are infinitely many numbers, many natural numbers, so that we can't verify the each and every number whether it is end with 0 or not. But if you apply the fundamental theorem of arithmetic, we can easily say that we can easily verify that either 4 power n can be end with 0 or not. How? See that 4 power n. So 4 means if it is a 4 power n, this is base and this is power. 4 can be expressed as what? 4 can be 2 into 2. So 4 factorization. So 4 factorization is unique. So 4 factors only 2 and 2. There is no other factors other than this, because from the fundamental theorem of arithmetic we know that this factorization is unique. So no other numbers cannot get 2 and 2. So only 4 can get 2 and 2. So that it has only factors 2 and 2. We understood that it has only factors 2 and 2. Now actually, if any number end with 0, like 10 end with 0, 20, 30, 100, 200, 500, these are all the numbers which are the end with 0. So these are all numbers end with 0 means we can say that it is every number is a factor of 10. Every number is a factor of 10. So that means every number contain the uh, 10 has factor. 10 factors are what? What are the 10 factors? 2 and 5. So that to get 10, we have to get the factors as 2 and 5. So there is a 10 factor. That means a number end with 0, it has factors 2 and 5. Then only the number end with 0. Otherwise, it never end with 0. So similarly here, whatever the power it is there, it's not important, but its number, the base should have the factors as 2 and 5, then only it end with 0. Since the 4 has no factors 2 and 5, it has only 2, it has no factor 5, so that 4 power n for any natural number, it does not end with 0. This is the one application part of the fundamental theorem of arithmetic, which we can conclude say that can say about 4 power n cannot end with 0. Like this, there is some other numbers, other problems, either 6 power n can end with 0 or 11 power n with 0. So there are some numbers like this. We will use it by using the fundamental theorem of arithmetic. Still there are some other applications from this theorem. For example, still we can find the LCM and SCF using the prime factorization method. The prime factorization is nothing but the fundamental theorem of arithmetic, because if we do factorization means the factorization part is nothing but the fundamental theorem of arithmetic. For example, there is a number 6 and 20. Suppose I want to find the SCF and LCM using the fundamental theorem of arithmetic. So fundamental theorem of arithmetic is nothing but we have to factorize each and every number. For example, 6 equal to 2 into 3. 20 equal to, we can write 2 into 2 into 5, because 2 2s are 4, 4 5s are 20. So that is 2 square into 5. So we are using the factorization, that is this unique factorization is there. So that's why this method is known as prime factorization method. So actually this is based on the fundamental theorem of arithmetic. Then how to find HCF and the LCM? So see that now select the primes of the 2 and 3 here, 2 power 1, 3 power 1, 2 square and 5 power 1. Then how to find HCF? Now we have to select the common primes first of all. SF means highest common factor. Here highest prime you have to select. Highest, not prime, highest common factor first of all select. Common factor is 2, 2. 2 power 1, 2 square. Whatever there, 2 is a common prime number. 3 is not common, 5 is not common. So we have to select 2. In this one, least one is what? 2 power 1 only. Because 2 power 1 is exist in the both. That's why it is common. 2 square cannot be taken because 2 square here exists. The 2 power 1, 2 square cannot be existed. So it is only 2 power 1. 2 square means 2 into 2. That means here 2 ones, 2's are 2 exist, 2's are 2 times. Here 2's are 1 time only. So 2 power 1 can be present in the 2 power 1, 2 square. So least one is what? Least one or common one is 2 power 1 only. The HCF is what? 2. So how to find the LCM? In the LCM, we have to find it by taking the each and every prime number. For example, if we take 2, in the 2, we have to select the highest powers of the prime number. Highest powers is what? 2 square and 2 power 1. We should not take both. We have to select any one, either 2 power 1 or 2 square. We have to select any one, because if a prime number is repeated in both, we have to select only one prime number which has highest power. Here 3 power is not present in both. If it is not present or it present one time also, we have to select the what is the highest, only one, 3 only. 5 also, because 5 highest power 5 only, 3 highest power 3 only, 2 highest power 2 square only. We have to select all the highest powers among all prime numbers. That product is known as LCM. 2 square means 4, 3 power 1, 5. That is how much? 4 these are 12. 12 5s are 60. 60 is the LCM. So for finding HCF, we have to select the common prime number. In this one also least power, so that 2 power 1 is the HCF. For LCM, select the each and every prime number so that which has highest power. So the product is known as LCM. Now take the, what happens if you multiply the HCF and LCM, what do you get? See that 2 into 60 how much? 120. Now what happens if you multiply 60 and 66 and 20? If you multiply 6 and 20, that's 60 into 20, 120. Now we have get the same result. So LCM and HCF 120, 6 and 20 also 20. So two numbers if we take, the product of LCM and HCF is 120, the product also 120. So we can say one conclusion that HCF into LCM of two numbers equal to product of the numbers. Product of the numbers. This is also one important result for LCM and SCF.